Welcome to today's paper reading. Today's paper is titled LLaMA Pro, Progressive Llama with Block Expansion. This paper was published on the AR14 preprint by Zeyu and colleagues from the University of Hong Kong, Arc Lab, Tencent PCG, and Beijing Language and Culture University. In the abstract, the authors highlight a significant difference between human skill acquisition and that of large language models, LLMs. Unlike humans, LLMs tend to forget previously learned skills when acquiring new ones. To address this, the authors propose a novel post-pretraining method that involves expanding transformer blocks and tuning them using only new corpora. This approach aims to efficiently and effectively improve the model's knowledge without compromising its existing capabilities. The paper introduces LLaMA Pro-8.3B, a versatile foundation model derived from LLaMA 2-7B, which excels in general tasks, programming, and mathematics. Both LLaMA Pro and its instruction-following counterpart, LLaMA Pro-Instruct, demonstrate advanced performance across various benchmarks, outperforming existing open models in the LLaMA family. This research underscores the potential of LLMs as intelligent agents capable of reasoning and addressing diverse tasks, providing valuable insights into integrating natural and programming languages for the development of advanced language agents. The introduction of large language models, LLMs, has significantly transformed the field of natural language processing, showcasing remarkable proficiency across a wide array of real-world tasks. Despite their versatility, LLMs still exhibit shortcomings in specific domains such as programming, mathematics, biomedical, and finance. This limitation hinders the development of generic language agents for broader applications. Existing research has attempted to enhance the multifaceted capabilities of pre-trained LLMs through tailored data recipes, but these methods require substantial computational resources and vast amounts of data. Consequently, domain-adaptive pre-training has emerged as a focus, demonstrating efficacy in adapting various LLMs to specific domains with reduced computational costs. However, a significant obstacle in catastrophic forgetting arises, where post-pretraining often leads to a decline in the model's original general abilities. To address this, the authors introduce a novel post-pretraining method called block expansion, which injects domain-specific knowledge into LLMs while preserving their general abilities, thereby enhancing their comprehensive capabilities. Figure 1 illustrates the superior performance of LLaMA Pro-Instruct across a broad spectrum of tasks, from general language understanding to specialized domains. This model achieves state-of-the-art results, outperforming other models within the LLaMA series. The key takeaway is the model's ability to maintain high performance in both general and specific tasks, demonstrating its versatility and effectiveness. Recent advancements in large language models have significantly improved performance across various tasks, driven by the growth in model and data scales. Generalist models have been developed to address a wide range of problems and adapt quickly to new tasks. The open-source community has also played a crucial role by releasing powerful models like LLaMA and CodeLLaMA. Our work builds on these advancements by specializing LLMs in the code domain. Post-pretraining typically involves a two-step process: general domain pretraining followed by domain-specific training. Fine-tuning aims to enhance instruction-following abilities or align model outputs with human preferences. Parameter-efficient tuning methods like adapter and LoRa are often applied during the instruction tuning phase. Our focus is on enhancing LLMs by increasing their depth during continued pre-training. Progressive learning has gained attention for accelerating large-scale model training. Methods like stacking and depth expansion have been proposed to maintain general performance while adapting to specific domains. Our method utilizes depth growth to achieve this balance. Figure 2 illustrates the process of post-pretraining a large language model, LLM, using a method called block expansion. In Part A, the LLM is initially pre-trained on a vast unlabeled corpus, resulting in a model with robust general capabilities. The authors choose the off-the-shelf LLaMA 2 model for this purpose. In Part B, the model undergoes backbone expansion where new identity blocks are added. These new blocks are fine-tuned using a domain-specific corpus, while the original blocks from the base model remain frozen. After this post-pretraining phase, the model can be further fine-tuned for instruction tuning as usual. The LLaMA block is composed of a multi-head self-attention (MHSA) mechanism, a position-wise feed-forward network (FFN), with switch-gated linear unit (SWI-GLU) activation and residual connections. The block expansion technique introduces an identity block after each original block, initializing weights to 0 to maintain the output integrity. The training pipeline focuses on the post-pretraining stage, where the model is fine-tuned on specific domain corpora, enhancing its capacity for domain-specific knowledge while preserving general knowledge by fine-tuning only the newly added blocks. In this section, we present the key experimental findings. Firstly, the experimental settings involve constructing a dataset concentrating on code and math, utilizing the stacked up and proof pile 2 datasets. The base model, LLaMA 2-7B, is expanded to 40 blocks using an interleaved approach, trained for 15,900 steps, corresponding to approximately 2,830 GPU hours. Secondly, the pre-trained results show that LLaMA Pro effectively balances natural language processing and coding capabilities, outperforming its base model, LLaMA 2-7B, in general language tasks while maintaining competitive code performance. Lastly, the supervised fine-tuning (SFT) results demonstrate that LLaMA Pro-Instruct achieves state-of-the-art performance, enhancing the average performance of LLaMA 2-7B chat by 13.81% and surpassing widely used chatbots from the LLaMA community. Figure 3 provides a detailed look at the LLaMA block structure, which includes a multi-head self-attention (MHSA) mechanism followed by a feed-forward network (FFN) with switch-gated linear unit (SWI-GLU) activation. Part A of the figure illustrates the standard LLaMA block, while Part B shows the identity LLaMA block after an identity copy, where the output linear matrix is initialized to 0 to maintain the output from the base LLaMA model. This setup ensures that the expanded model retains the same output behavior as the original, facilitating domain-specific adaptation while preserving general capabilities. Figure 4 presents a comparison of LLaMA Pro's general performance and code performance against a range of models developed around the same time, from general-purpose large language models, LLMs, to those specifically designed for coding tasks. The size of the visual elements, or blobs, in the figure is proportional to the number of tokens each model was trained on. This comparison helps to illustrate how LLaMA Pro effectively balances its capabilities in both natural language processing and coding, offering insights into its performance relative to other models in the field. Table 1 presents a comprehensive comparison of evaluation results among several prominent code and language models. The data highlights that LLaMA Pro effectively balances natural language processing and coding capabilities, outperforming its base model, LLaMA 2-7B, in general language tasks while maintaining competitive coding performance. Conversely, CodeLLaMA 7B shows a trade-off, sacrificing general performance for enhanced coding capabilities. This balance achieved by LLaMA Pro is attributed to its expansion design, which preserves the initial LLaMA block's capabilities and adds more blocks to accommodate domain-specific knowledge. Table 2 presents the results of a GPT-4 automatic evaluation of various chatbot models, highlighting the performance of LLaMA Pro-Instruct. This model significantly outperforms widely used chatbots from the LLaMA community, demonstrating its capability to provide helpful responses. The evaluation was conducted using GPT-4 automatic scoring, as proposed by Vicuna, Ying et al., 2023, and the details of the empty bench can be found in the Appendix F. This performance indicates LLaMA Pro-Instruct's potential as a chatbot capable of delivering impressive performance in traditional benchmarks, in addition to its conversational abilities. Table 3 evaluates the model's ability to incorporate tools into its reasoning process. The effectiveness of this integration is gauged by the model's success rate across different interaction stages. Figure 5 illustrates the training loss analysis concerning the addition of varying blocks and mixture of expert (MO) expansion, alongside traditional training strategies like fine-tuning and LoRa. The figure shows that the training loss consistently decreases as more blocks are added, indicating improved performance. It also compares the effectiveness of block expansion with MO and traditional methods, highlighting the scalability of the approach with larger models and increased data. This analysis provides insights into the balance between general and domain-specific capabilities in large language models. Table 4 presents a comparison of the original Mistral 7B, Gemma 7B, and our Mistral Pro across various benchmarks from the Open LLM leaderboard. The data highlights that Mistral Pro achieves superior performance, particularly in the domains of code and mathematics. Notably, Mistral Pro scores 78.4 on GSM 8K and 30.3 on math, surpassing Mistral 7B's scores of 77.7 and 28.2, respectively. Additionally, Mistral Pro demonstrates competitive results compared to Gemma 7B while incurring significantly lower training overhead. Table 5 provides a detailed comparison of the evaluation results among various training strategies, focusing on their performance across both general language tasks and law-specific tasks. The table highlights that while different strategies impact performance, adding 8 blocks offers an optimal balance of performance and cost efficiency. This approach is particularly effective in enhancing domain-specific abilities while maintaining the model's general capabilities. Figure 6 illustrates the token distribution shift after block expansion in comparison to the initial LLaMA 2-7B model. The figure categorizes tokens into unshifted, marginally shifted, and significantly shifted, with percentages of 92.6%, 6.8%, and 0.7% respectively. Additionally, frequently shifted tokens are listed below the main distribution data. This analysis helps in understanding the impact of block expansion on token distribution within the model. The scope of this study is confined to the language modality, specifically focusing on programming languages and English. The block expansion method developed in the study aims to balance general and domain-specific capabilities in large language models. Future research directions include extending the application of this method to other domains such as multimodal large language models and multilingual domains. In this study, the authors introduced a novel block expansion method for large language models, LLMs, post-pretraining. This method aims to enhance domain-specific abilities while preserving the original general capabilities. The approach effectively balances the model's performance across both general and domain-specific tasks. The effectiveness of this method was demonstrated through LLaMA Pro, an LLM initialized from LLaMA 2-7B with 8 added blocks, which outperformed other LLaMA series models on comprehensive benchmarks. Additionally, the authors discussed the ethical implications of their work, emphasizing responsible AI development and its impact on society and industry. The LLaMA Pro and LLaMA Pro-Instruct models are designed to handle a variety of NLP tasks, with a particular emphasis on programming, mathematics, and general language tasks. These models are intended for scenarios where integration of natural and programming languages is required. While LLaMA Pro addresses certain limitations of previous models in the series, it may still face challenges in highly specialized domains or tasks. Users are advised to be aware of potential biases in the model and to use it responsibly, taking into account its impact on various applications under the LLaMA 2 license. Thank you for watching.